Good morning, everybody. And I'm sorry I cannot attend the conference personally because I'm sure it's going to be an excellent one. And at least I want to thank the members of the organizing committee for inviting me and making it happen even by Zoom. So I have 20 minutes, so I will make a brief presentation about shock attenuation of methyl cellulose hydrogels and how briefly do we experiment with that and how do we model the attenuation. So the motivation first, well, we all know that when you have a shock wave, whether it's an explosive or shock blast wave or an impact, in the case when there is no penetration and no bodily obvious damage, the wave can still be very, very significant and can create a lot of injuries inside the body, like traumatic brain injury, for instance, where the head is not open, but the brain is completely damaged. So we would like to find a material that can mitigate the shock wave, the stress wave, in the case of a non-penetrating impact. And okay, so for that we chose, for the past 10, 12 years, water-based methyl cellulose solutions. So what is that? Methyl cellulose is a hydrogel, it's a polymer with an interesting property that it undergoes the so-called inverse freezing. So this is basically liquid at room temperature, where when you heat it, it solidifies, which is contrary to most materials that we know. And this is an endothermic process, so it absorbs energy during the solidification. MC gels don't have any memory effects, so they can be shocked and reshocked again, and they don't remember what happened to them before. And last but not least, those materials, MC gels, are safe, they're non-toxic. In fact, they're used in the food industry to prepare glazing on cakes and so on and so forth. So they're not allergenic and they're cheap. Okay, so the question we ask is, in fact, in a nutshell, how does the thickness and the concentration of the gel affect the impulse attenuation? So next, we want to develop an impulse attenuation model for aqueous methyl cellulose solutions that could predict the outcoming signal and eventually implement that in a finite element model so that we can design a protective system which includes a layer of gel. And other than the momentum attenuation, we also want to know the energy attenuation behavior, and I will elaborate on that. So how did we prepare? Well, this is a cooking recipe. You take the gel, you mix water, you heat it, you cool it, and you do whatever the colleagues, the chemistry colleagues tell you, and at the end of the day, you obtain an opaque gel like that, which is liquid and kept in the fridge at 1 to 4 degrees C. And I must say that it solidifies at around 70 degrees Celsius. So most of the time it's liquid, and this is the phase in which we will test it. The experimental setup. Well, experimental setup is pretty simple. It in fact consists of a Hopkinson bar, a set of Hopkinson bars that you see here, and you don't see the other one. But the problem is that the gel is a strongly attenuating material, so you cannot use the regular Kolsky setup. And for that, we use on each side of the gel is going to be inserted here, the liquid gel between the plates, and we use force sensors made by FlexiForce, which directly measure the force on both sides of the gel. The vessel is adjustable, so we can change we can vary the thickness of the gel layer. That's all, very simple. Of course, when you shoot the striker, you get the stress wave. I'm sure that this is not the right community to explain such things. And the FlexiForce, they're very convenient because they're cheap and they're pretty reliable to measure directly the force on both sides of the gel. So 2 parameters were tested, the gel thickness and its concentration. The thickness, we tested 4, 7, 10, and 20 millimeters. The concentrations, we tested 0, 5, 10, and 15%. 0 is water, and water will always be here as a reference fluid, or as a reference material, to which we'll compare the results of the gel. Okay. Typically, that's an incoming and incident and transmitted signal. You can see force signal in Newton. You can see that the transmitted force is significantly lower than the incident force. So you have an attenuation of the signal, but not much you can tell about. And I would say that when we started with measuring the peak force, it's of course very nice to measure the peak force, but it's not very instructive. So it's better to integrate this pulse, the force over time, get the impulse, and that's much more reliable as information. So now I want to show you the power spectra of the incoming and outgoing signals. It's very important. We'll have to work in the frequency domain because we want to know which frequencies are attenuated and how they are attenuated, and all that in order to generate a model. So not just the impulse, but also the frequency content of the pulse is very important. So, well, use this simple formula of the calculating the impulse, which is the integral of the force over time, and just making the impulse out, or impulse in minus impulse out, divided by entering impulse, and that's the percentage of attenuation, of impulse attenuation. Okay. So impulse attenuation, as I said, is less sensitive to measurement noise than just the peak force. The peak force is a punctual or point measurement, whereas the impulse is an integral measurement. Okay, so those are very loaded diagrams. So just look at them simply. Those are various thicknesses of 4, 7, 10, and 20 millimeters. Those are various compositions from 0 to 15%. Black is the water, and in the water, the attenuation is the least. And generally speaking, as you increase the concentration of the gel and the thickness, you get a better attenuation of the signal. So I don't have too much time to dwell on those graphs. This one is a little bit abnormal, I should say. But other than that, you see a general trend to attenuate the signal with concentration and with the thickness of the layer. So the impulse attenuation depends on concentration and thickness. Okay, now let's go to the frequency attenuation. So you can define a frequency response function, h tilde of f, defined as the Fourier transform, or ratio of Fourier transforms of the convolution of the incident and outcoming signal divided by the autoconvolution of the incident signal. That's the mathematical definition of the transfer function, or of a material. So now when you look at the frequencies, and this is water, 5%, and 10% and 15%, they all have more or less the same shape of decreasing and then coming back. Various thicknesses that you can see, 7, you can see water, and then the 15%, and various thicknesses, but in fact the thickness is not very important here, but we will have to average those results if we want to get a meaningful function. Those are the average frequency response for concentration. And then we know that what we observe, that the impulse attenuation is thickness and concentration dependent without any frequency response. As I told you, the graphs are more or less the same. The frequency attenuation is frequency dependent. That's very important. So it depends on the frequency content of the signal, but luckily it's not thickness and concentration dependent. So we can separate the frequency attenuation and the impulse attenuation. And now we need to combine both if we want to have a model. So this is the thickness, T is the thickness and the concentration. So this is an equation we fit for the impulse attenuation. This is another one in which we use an error function to describe this decreasing curve for the frequency response of the gel. We combine both, and this is what we get. We have in blue the incident signal, in red the pulse after frequency correction, and finally, after impulse correction, since those are separate things, we scale the outcoming signal. And now let me show you the bottom line. This is the bottom line. 3 experiments, 5%, 20 millimeters, 10%, 4 millimeter, 15%, 20 millimeters. In red, you have the experimental signal, the experimental transmitted signal, and in black, you have the model prediction. I hope you'll agree with me that the prediction of the model is fairly representative of what we measure. So we are confident that we have a 1D. For the moment, it's a one-dimensional model that represents the shock attenuation of the methylcellulose hydrogel. That was published in Mechanics and Physics of Solids and in 2020, and we're still working on it. I will update you. Now let's go to energy attenuation. Energy is not impulse, as we all know. Energy is a different thing. So what we use here is a very simple setup. Again, the incident bar, the recipient with the gel, but now we're using a sort of version of the ballistic pendulum. In fact, we're measuring how much this momentum trap is flying away. What is the velocity of the momentum trap? We process the images, and we have the energy in, kinetic energy out. So basically, with this complicated formula, the ratio of the kinetic energies is the energy transfer or the energy absorbed, 1 minus. Yeah, so the energy transfer, the energy of the trap divided by the energy, the incident energy, kinetic energy. But kinetic and strain are equal, so that's no problem. And this graph shows you the transfer of energy for different concentrations and one thickness, only one thickness. So that's water and 5%, 10%, 15%. So basically what you see is that there's no need to go to very high concentrations where the material gets, in fact, very viscous. And one of its advantages is that it's fluid, so you can cast it in any protection system. But when it's too viscous, you cannot work with it. So anything between 5 and 10% would be okay and would mitigate the energy by some 25%. So the conclusions of this brief talk. Methylcellulose are potent shock energy absorbers, and impact momentum has been modeled as a function of concentration and thickness. And we are pursuing this work now in full 3-dimensional modeling using finite element. This is not a piece of cake, to be honest. We've been working on that for over a year, but the results are slowly but surely coming out, in which our goal is to model any impacted system by a bullet or by a shock wave and see what's going on the other side. Energy attenuation is higher than water, and it reaches saturation at around 10%. We said that. Now, the energy calculations are affected by the setup, because you have a setup. Part of the setup is conducting the wave, and the other part is going through the gel. So this is a problem that we have solved now by entirely new design and calculations, in which we can overcome the limitations of the gel container. So this work is also in advanced steps. And had we had this conference a couple of months later, I would have presented more recent updates on that. I want to thank my sponsor from the Israel Ministry of Defense, my colleagues from chemistry, Yoav Eishen and Galit Parvari, who introduced us to MC gels. My former student, Dr. Rothbaum, to whom I send special thanks and thoughts in the special situation we're in. Batren, who is now working in the industry, and she finished her master's. Orel, who's working on the PhD and the numerical modeling, and Linoy, who was an undergrad assistant. And most of all, I would like to thank Dr. Yael Demarty for inviting me and making it happen in spite of the distance and the technical difficulties. Well, I hope I have made it in time, and I want to thank you for your attention. And I would like to meet you personally. Unfortunately, I can't. And those are the papers that were published in relation with the gels, and feel free to get more details than my very brief presentation on the subject. Thank you very much.
Thank you very much, Danny. I don't know if you can hear me right now from here.
I don't hear you very well, but
I think I have to use this microphone. It's better right now.
yeah, now I can hear it.
Thank you, Danny. It's a very nice presentation. I'm really not very familiar with those type of materials, but I found it very, very interesting. I don't know if somebody in the audience will like to make a question. We have a microphone over there. Is there anybody here in the audience who? Well, I think at this moment everybody is still asleep.
Yeah, that could be. That could be.
Yeah, it could be.
Yeah, that could be.
Yes,
but you have good schnapps. You have good schnapps in Colmar.
Yeah, we have a question. Let's think it.
Thank you very much for a great talk. In terms of your energy absorption, have you?
I don't hear. Sorry, I don't hear.
Maybe you can get here to this microphone to make the question.
Hi, thanks for a very great talk. On your energy absorption, have you measured any loss tangent on the transition from liquid to gel? And have you related that to your energy absorption in your wave transmission?
Regarding loss modulus, if that's what you are referring to, that has been done and reported early on those gels. But people have used essentially very small amplitude, like the rotating disk and the classical rheology measurements that are irrelevant to the shock experiments that we're doing. So we didn't measure any loss modulus.
But it's the loss tangent, which is the ratio of the loss modulus to the storage to loss modulus.
Right, right. But we didn't measure it.
Absorption.
Well, this is in fact this loss modulus is a measure of viscosity and of course energy absorption. So it's inherently present in the experiments and in the results, except that we have not attempted to measure it because under shocks there is no real classical way to measure it. So this is done under static loading or very small vibrations usually for polymers.
Thank you.
My pleasure.
Thank you very much. Do we have any other questions from the audience? So I want to thank you very much, Danny, for being with us. I know that those are difficult moments for you and your country, and I hope you the best. Okay.
Thank you very much for your kind words. And I'm afraid I will not be able to stay for the 3 days connected, but really from all my heart, I wish you, each and every one of you, to have a fruitful and enjoyable conference, and I'm sure it will be. And I really regret I cannot be with you today, but there will be a rain check. You will see me again, I hope. Bye-bye.
Thank you very much, Danny, again. And well, let's continue the conference, and then we are going to proceed with the next talk. Okay. Thank you, Danny, again, and see you soon.
See you soon. Abrazo.